Good day and hi, I am Suraya Zainuddin from University Technical Malaysia, Melaka, Malaysia. We'll be sharing on a paper titled Doppler radar-based pothole sensing using spectral features in KNN. So this is my paper title, and this is the list of author. Okay, I'll start with the outline of the presentation. I will start with a brief introduction, followed by a problem statement and the objectives. And next is the proposed method, result and analysis, and finally, conclusion. What is potholes? Potholes basically caused by a weakening soil and aging asphalt, which significantly reduce the road safety and increase the strain on government entities responsible for road maintenance. In Malaysia, particularly in Selangor State itself, around 50,000 potholes were reported between year 2019 and 2020, which led to a decline in road quality and a rise in traffic accident. Table 1 introduces various technology available for pothole detection, summarizing their performance. The methods include radar-based, vision-based, acoustic-based, vibration-based, and laser-based, each with varying in terms of accuracy, cost, and the ease of implementation. Let's look into the problem statements. The issue is basically in the limitation of different pothole sensing technology, such as vision-based and laser-based sensor. This sensor may struggle in adverse environment, limiting their effectiveness in detecting potholes under challenging conditions such as poor lighting or weather. Meanwhile, acoustic-based sensor, more affordable. They have difficulty distinguish between different type of road obstacles, making them less reliable for precise potholes detection. And vibration sensor, this type of sensor face challenges in identifying minor flaws and are constrained by battery life, making them less suitable for long-term and continuous operation. Additionally, this paper proposed the utilization of Doppler radar. The well-known challenges of using Doppler radar for pothole detection, such as the inability to measure depth and difficulties in distinguish between echoes from the target and surrounding element. This issue underscore the need or the requirement for more advanced sensing method, like combining machine learning and the radar system in order to improve potholes detection accuracy. Hence, this led to the primary goal of the research. The key objectives are divided into two. The first one is to explore the K nearest neighbor KNN models. This research aims to apply the KNN model to improve the pothole detection by classifying road condition. This is done by analyzing feature extracted from the Doppler radar power spectral density PSD plot. And the next one, second one, is evaluating the sensing performance, which to assess the effectiveness of utilizing Doppler signal in detecting potholes. Okay, this slide presented the experimental setup and the approach used to detect the potholes. The key element here is the placement, the radar placement, in which the radar is mounted on a moving vehicles here. With the radar position at the height of 1 meter and inclined at 45 degrees. Vehicles move at 30 km per hour speed over an asphalt surface to capture data. From the waveform type utilized for this particular exercise is the continuous waveform at the operating frequency of 24.125 GHz. The data collection is basically taken over 10 potholes, which iterated 10 times each per pothole, and resulting in 44% potholes data and 56% of non-potholes data. In this particular setup, we introduce a distinct viewpoint by placing the radar on the moving vehicles, where the radar is moving despite the subject of interest. Okay, so For the signal processing, the radar data is basically segmented into 1000 points and processed using discrete Fourier transform with 256 point, which is used to analyze the Doppler radar signal. The segmentation is meant to unify the signal in order to avoid the bias by longer signal. PSD analysis was conducted in which the Doppler audio signal are processed to extract the feature from the PSD plot, and this analysis provides the spectral features needed to classify the root condition, focusing on the detecting potholes. This figure 2 basically is the block diagram of the proposed pothole sensing and classification. We fed the raw signal from the Doppler radar to the signal processing block. Here, under the signal processing block, the signal is filtered and denoised and sent to the signal segmentation for the chunking into 1000 point segmentation. The segmented signal is then passed to the PSD processing. Under this particular block, the signal is the PSD is generated, and the statistical analysis was conducted from the PSD plot. The feature is extracted, and the extracted feature is submitted to the machine learning block. Under the machine learning block, the data splitting was 80-20, 80 for training and 20 for testing, applied under 6 KNN model with PCA enable. The PCA enable is to avoid the overfitting of the data. And finally, the performance evaluation was conducted in terms of accuracy and also the confusion matrix. Okay. On the left-hand side, figure 3 depicted the PSD of the Doppler signal. This PSD is basically hardly to distinguish visually between potholes and non-potholes. And on the right-hand side, summarize the PSD spectral analysis conducted. We have centroid, spread, skewness, kurtosis, entropy, flatness, and roll-off. Briefly, the spectral centroid represent the center of mass of the power spectrum. The spectral spread watch the breadth of the power spectrum distribution. Spectral skewness presents power spectrum distribution asymmetry. Spectral kurtosis measures the tailness of the power spectrum. Spectral entropy evaluates the variation of frequency in radar by describing the randomness in the power spectrum. Spectrum flatness measure tonal characteristic in the spectrum, and finally the spectral roll-off provides the frequency at which a specific percentage of the spectral energy is concentrated. Basically, the spectral analysis provide a detailed comparison between potholes and non-potholes road condition, with the data showing the pothole surface cause significant changes in the spectral features. This difference in PSD signature helps to classify the road condition and emphasize the importance of accurate detection for road safety and maintenance. Okay, so this is under result and analysis. The blue this is the spectral centroid plot. So the blue line indicates the non-pothole and the red indicates the pothole. This data is taken over 100 samples. Okay, the spectral centroid basically represent the center of mass of the power spectrum. In the non-pothole scenario, the blue line, the centroid has a concentrated distribution with a higher mean and lower standard deviation, which indicates a stable road condition. Meanwhile, in pothole scenario, this red line, the centroid display a broader spread with a lower mean and higher standard deviation, which suggesting more variability and disturbances in the acoustic landscape due to the potholes. Okay, this is the spectral spread analysis plot. From the spectral spread analysis, the non-pothole show more consistent and stable audio characteristic with a lower mean and standard deviation. Okay. while the potholes road have a wider range of frequency variation, indicating the large surface irregularities caused by the potholes, highlighting the distinct audio signatures associated with this road condition. Okay. Next is the spectral skewness. Under this spectral skewness plot, the road with potholes, the red one, exhibit a higher mean skewness and larger standard deviation, indicating a bias toward higher frequency, which is indicative of a sharp deviation like potholes. Meanwhile, for the non-potholes road, in contrast, it shows more balanced energy here, distributing with fewer deviation. Okay, for spectral kurtosis analysis, potholes, the kurtosis value are higher, with larger deviation, suggesting the impulsiveness event linked to the potholes, while the non-potholes road show more moderate clustering pattern here. Next is the spectral entropy plot. For spectral entropy plot, non-pothole road show relatively stable and normally distributed entropy values, indicating a consistent road condition. Meanwhile, for the pothole scenario, this is the pothole line, have higher variability in spectral entropy, which reflecting the unpredictable road condition due to pothole. Spectral road of analysis shows that non-pothole road focus on higher frequency, while potholes road covering a broader spectrum, especially in the mid-range frequency. And for the spectral flatness plot, non-pothole exhibit a stable audio signal with consistent flatness value. Here you can see the result is doesn't have too much whereas the potholes road show a greater variability here, correlating with the presence of potholes, the instability of the road surface. Next, the assessment also has been conducted over a machine learning analysis. On the left-hand side, we have the confusion metric for 6 KNN model, presenting under figure 11, comprises of the co-S KNN, cosine KNN, cubic KNN, fine KNN, medium KNN, and also weighted KNN. Basically, a confusion matrix helps us to visualize the performance of the classification model by comparing the predicted label with the actual label. It highlights the true positive, false positive, true negative, and false negative results. Different KNN model are evaluated to see how well the classifying of potholes and non-potholes condition based on the Doppler database. The 5KNN model performed the best, which is highlighted by its superior classification accuracy here. Okay, basically, 5KNN have the number of neighbor 1, with the distance matrix of Euclidean, and during the training, it achieved the accuracy of 89.58%, and during testing, it achieved up to 95.83%. In over here, we can see that the fine-tuning the model, particularly the K, the neighbor value, improve the ability of the correctly identify the road condition. The research focus on the balancing of the trade-off between the underfitting and overfitting, optimizing the key value, ensure the models can generalize well the new data without being too sensitive to noise, leading to more reliable classification. In addition, from the finding, we also can see that the choice of algorithm significantly influence the model's capacity to accurately classify road condition. The evaluation underscored that the different variant of KNN have varying level of effectiveness depending on how well they handle the noise and identify the pattern in the data. Overall, the research aimed to develop the machine learning model for classifying road condition using the data, focusing on differentiating between potholes and non-potholes condition. The process involved the processing of audio data from the radar sensor, which mounted over the moving vehicles, and to extract the key audio features through the power spectral density analysis. Next, a comprehensive analysis of various K nearest neighbor KNN algorithms variants was conducted to process the audio data from radar. And the outcome is that the 5 KNN emerged as the most successful by achieving 95.83% accuracy. This research highlight the potential of the machine learning in accurately categorizing road condition, emphasizing the role of algorithmic choices and the parameter optimization in achieving the precise results. This result was funded by a grant from University Technical Malaysia Melaka under the grant number of PJP 2022 FTKEE S01881. And here we would like to take this opportunity to thank Teknologi and Kejuruteraan Elektronik and Komputer, University Technical Malaysia Melaka, and also Research and Innovation Management Centre, CRIM of UTM, for all the support. With this, I end the presentation. Thank you.